There are roughly 1,400 living species of bats, maybe even more than that. Now they seem to add a few more every year as genetic studies develop. And so they make up about a fifth of all living mammals in terms of the number of species. And as you can see, they come in a variety of sizes and shapes, and they do a lot of different things. Bats typically, you think of them as eating insects, but they also eat different kinds of foods, and they are active at different times in the evening, and they fly in different ways. And so there's a lot of diversity in morphology and in behavior in this group. Most of them are really small. They're on the order of maybe 100 grams, which is not very much, basically. And so you can see here's a sort of a typical sized bat on this woman's thumb here. There's another one in someone's hand. So they're very tiny, except there's a few that aren't so tiny. Occasionally you get a big fruit bat. This is an animal called Pteropus. They live in Southeastern Asia and Africa today. I think this woman is pretty small because they are big, but they're typically not that big. So this goes in the order of about 2 kilos, give or take, something like that. And that's about as big as bats actually get. So for the most part, they're pretty small animals. And this is a size, just to show you a size distribution of modern bats today, and the median size is about 14 grams, basically, so very small, including things as tiny as 2 plus grams. Crocionicterus, which is the bumblebee bat from Thailand, and it really is smaller than your thumb. It's a very tiny little creature. So as we'll see, there's some reasons why bats are small for the most part in a minute here. One of the oddities about bats, and this is going to come back in this talk as well, is that if you look at sort of a distribution of the body size of animals versus how long they live, typically as you get towards larger sized animals, the life expectancy goes up. So elephants are up here at around 60 plus years of longevity. Humans sort of cheat the system because we have culture and drugs and stuff that keep us alive probably a lot longer than we typically would be otherwise. So we probably would fall out down here somewhere if we weren't involved in taking care of ourselves and with improved medical technology. So, but what's interesting is here's small mammals down here, and here's bats way up here. So bats, even though they're very small animals, oftentimes live for a long time. They can sometimes live up to 40 or 50 years. And so it has a lot to do with their metabolism, which we'll see in a minute. And it's an interesting phenomenon that is part of what makes them an interesting group of animals. So you've heard this expression many times, blind as a bat. Well, bats are not blind. Bats see pretty well. All of them see at some level. One of the things everybody asks me about are vampire bats because everybody wants to know. And this is a Desmodus here. It's a fairly small animal as well. The bodies are about this big, so they're not terrifying at one level. But they are, they do feed on blood, and they live in South America and Central America. Mostly feed on cattle and some other ungulates that live in these areas. And they spend a lot of time scurrying around on the ground and nicking the legs of cattle and with these very sharp teeth in the front here. And they also exude, when they cut you, an enzyme that prevents blood from coagulating, so the blood flows out more easily and can pool up on the ground, and then that's how they eat, is off the ground, basically, when the blood is sort of pooled up. I did several projects in Belize in the last few years, and we capture a lot of these guys. They're really common there. And most of the bats you'll find in South America, there's a lot of variety, are pretty pleasant animals. They're very calm and not very intimidating. These animals are very nasty. They don't really like anybody. They don't really like anything, and they'll try to bite you. And you can get bitten and be bleeding before you even know it. So we take a great deal of caution with them over the time that we work with them. But they really are very fascinating because they spend a lot of time on the ground, and they walk around in ways that you wouldn't expect a typical bat to behave. And so they do things that are atypical of bats in general. And finally, bats don't fly into your hair. They just have no interest in being there. So, the last place they would ever want to be is in your hair. So trust me, that just doesn't happen unless you want it to. Okay, so other things. Bats are generally pretty clean. They groom themselves a lot, even though they live in large colonies. Sometimes they still maintain a lot of hygiene, or as much as one can. And you hear a lot of talk about bats being vectors for rabies and other diseases, and it is true that they are, but it's really not as prevalent as one would think. In the U.S., over the last, between 1997 and 2006, there was only 17 confirmed cases of bats causing rabies, and so that's less than 2 cases a year over a 10-year span. So not a big problem, even though it is true that they can carry some diseases. Okay, so that's just kind of boilerplate information about bats that you can take home and tell your friends, I know trivia about bats or whatever. So does anybody know how many bat species live in Alberta? Any guesses? 1, 10, 100? All right, well, I'll just show you then. There are 5 different species of Myotis that live here, these guys. Most of them are fairly common except this one here. This is Myotis keenai, which lives only in the very eastern part of the province, but otherwise the rest of these, in the summer evening, even though you might not be able to tell them apart when you look up in the sky and see them flitting around, there are a multiple number of species of Myotis that live here. There's a species of silver-haired bat that lives here. And in fact, Lazanicterus is pretty common all over North America. It goes all the way up past Edmonton, and so it survives well into the Arctic areas. Aptesicus, the big brown bat, is also here and is pretty common in North America as well. And then there's 2 different species of Nycteris that are rarer but still here. So in total, there's 9 different species of bats that survive here in Alberta and thrive for the most part. All of these are hibernating forms, so right now they're probably all still asleep, but should be starting to wake up pretty soon as the snow stops and it starts to get a little bit warmer. So that sort of brings us to where you find bats in general, and there's 2 different varieties of bats I'll talk about in a minute. I showed you a picture of the large pteropodid bat, the large fruit bats, and their range really is in this red rectangle, basically tropical parts of the Old World, and they've never, as far as we know, ever occupied any place in the New World, and there's no real fossil record of them, so it's hard to know what their extent was in the past. The sort of yellow rectangle encloses the distribution of virtually all other bats, the microchiroptera in quotes, the echolocating bats. And you can see there's almost no place that bats don't live, except for the very, very highest latitudes in the north and south. They occupy pretty much everywhere, maybe a few isolated islands out in the oceans that are hard to get to. But for the most part, they have a global distribution and are amazingly diverse, as diverse, more diverse than any other group of mammals except for rodents. And so a big success story in a lot of ways. Okay, so just a few facts about some of the bats that live today. These pteropods are flying foxes, fruit bats, I called them earlier. I mentioned the Old World tropics, and there's about 42, 43 living genera still. A lot of them are under duress. A lot of them are just like the Malagasy lemurs endangered, but they are still fairly well distributed across most of the tropical Old World. Like I said, there's almost no fossil record. There's only 1 extinct genus that's been described, and a couple of sort of references to fossils of modern taxa, but for the most part, no fossil record to speak of, which is unfortunate because I think it would be very interesting to know. And this is part of the reason I've been in Indonesia for the last 5 summers trying to find a fossil fruit bat, but to no avail yet. Haven't given up. And for the most part, these bats don't echolocate. They kind of, a couple of them have a sort of a rudimentary echolocating system where as they fly, they tip the tips of their wings together and they make a little slapping sound, and they can detect as the echo from that comes back to them. They can hear it, and if they're close to a large object or something, they can use it. But they're not really precise echolocators like the smaller bats are. For years, these were called Microchiroptera and used as a sort of a subordinal level designation. But as it turns out, as with most everything, once you start looking at the genetics, you discover that these really aren't monophyletic groups, and so there's some complexity here. So Microchiroptera is now in quotes, but it still sort of is a good way to refer to all of the echolocating bats that live in the world today. And you can see they're pretty much cosmopolitan, as I mentioned, distributed all over the place. There's at least 136 extant genera. I'm sure there's more than this. The slide's about 4 years old, so it's probably up to 150 living genera now, and almost 1,400 or 1,500 living species. There's a lot of fossils, believe it or not. There's a 40-plus extinct genera that have been described, and as far as we can tell, virtually all microbats that we know of, past and present, were echolocators. Okay, so there's characteristics of the bat skull, which I'm not going to dwell on, but just to mention them briefly. All of these characters, cochlear enlargement and loosely attachment to the skull and various things like this, all have to do with echolocation. So echolocation is a very important part of the behavior of modern bats, except for the fruit bats. And so all of these things that are unique to bats, that are really the shared derived characters that define the groups, are related to that phenomenon. Bats are remarkably diverse morphologically. This is one family of bats, the Phylostomidae, mostly from South America. This is the vampire bat over here. But you can see the whole difference in designs of skulls and jaws that define just this one family is really quite remarkable. From nectar-feeding bats over here to blood-feeding bats here, to fruit-eating bats down here, to flower-eating bats over here. I mean, they do a lot of different things. And because of that, their morphology, the shapes of their skulls and the way in which they're put together reflects the kinds of things that they do. So mostly having to do with diet and with echolocating features. Okay, so and then there's the features that we would all kind of recognize as being bat-like things. So there's this flight membrane or patagium that's present. Every bat has a flight membrane of some sort. There's elongation of fingers and loss of claws. Some other parts of the skeleton are specialized in various ways. All of these having to do pretty much with being able to fly. So the modifications of the skull having to do with echolocation, and the modifications of the skeleton having to do with flight. And so here's a patagium. These are the fingers that are used to support the flight membrane. So unlike birds, which don't really have any fingers left, and have a different kind of arrangement of their wings, these guys use the fingers to support the patagium. And this is just a skeleton to show you the elongate fingers, mostly, and the loss of the claws at the end, except for on the thumb and various other things. And there's a lot of modifications of the shoulders, especially, and the chest that have to do with flight musculature that are different in bats than anything else. And of course, because, as you all probably are aware, bats hang upside down when they rest, there's a lot of changes that have happened around the hips and the knees joints as well to change the way in which the support mechanism of the bones is designed so that it's more easily supports a hanging or an extensive force versus a compressive force on the bones. So there's lots of little things that change over the course of evolution to produce the things that make bats unique, basically. Okay, so we now know a little bit about living bats. What about the fossil record? So first of all, where do bats belong in the mammal tree of life? For a long time, we thought bats were pretty closely related to primates, and morphologically, in some ways, you can still sustain that notion. But generally, based on a lot of molecular data now, bats tend to fall out over here, Chiroptera. This is the order that bats belong to. Chiroptera simply means hand wing, and as we saw why a minute ago. And they are now grouped in a whole large clade called Laurasiatheria, which includes things like carnivores. Pholodotans are kind of funny creatures. They're pangolins, these scaly anteater-looking things. And then parasitactyls, horses and tapirs and stuff, and seed artiodactyl, which is whales, and all of artiodactyl, deer and sheep and goats and things like that. So they seem to be members of this clade, or in some cases they fall out with eulipotyphilans like hedgehogs and shrews and moles and things like that. But they don't seem to be members of this other sort of great clade of mammals, the Euarchonta glares, which we thought they were at one time. So, and this is pretty consistent. I mean, this happens fairly consistently. Now, oops, let me back up just for a second. The other thing that's to notice here is that we have bats, the predicted range of bats. If you put this tree of life on a time scale, the origination date of bats goes back to somewhere around 65 million years, give or take. So keep that in mind as we go through here, that the molecular data is telling us that bats must be at least 65 million years old based on this arrangement. This is a fairly old analysis, but it's been upheld by more modern ones recently. So it still seems that bats as a group molecularly go back quite a ways. There's a pretty good phylogeny of bats that's been worked out by molecular data. I won't obviously dwell on this, but you can see there's a lot of different taxa, and we know pretty well the relationships of bats within the order, with some minor exceptions here and there. So what about through time? Well, the time period we're looking at really that we want to focus on is this time from about 65 million up to probably about 45 or 46 million, because we know for sure that bats appear in the fossil record by about 51 million years ago. We have skeletons, so we know they're bats, and there's no doubt about that. Before that, there's a few bits and pieces of potential bats that show up before that, a little bit earlier, but we really lack any kind of record from the Paleocene for bats whatsoever, and we'll come back to that at the end of the talk and revisit that when we try to figure out where bats came from. So there used to be 10 extinct families of bats, but we just added a new bat family recently. It hasn't even been published yet, but it will be pretty soon with some colleagues from New York down here. And so there's 11 extinct families of bats that we know of that have been described so far. And a lot of these you probably have seen pictures of before. So I will talk a little bit about these. I think Kevin Seymour was here a few years ago and talked to you about Echolocation. We're going to have to go back to Echolocation for a little bit because it's an important taxon in the sort of our understanding of how bats develop. But in a way that's a little bit odd almost, the oldest known bats that we have are also some of the most complete bats that we have, and this is mostly just because of the circumstances of their preservation. So this is an animal called an Icaronicterus, that came from the Green River Formation in Wyoming, and this was described in 1966 by Glenn Jepson, and it was really, at that time, by far the best known fossil bat from North America, certainly, and one of the best known in the world, and it really was exquisitely preserved. This specimen is extremely delicate, and it's quite small. I don't have a scale on here, but the body itself the whole animal is about that long, and so it's quite small, but very beautifully preserved in these lake beds from the Green River Formation in Wyoming, dated to probably somewhere around 52 million years, give or take, something like that. And for a long time, that was really the only decent fossil bat we had from North America, except for things that are pretty young. But in Europe, there was others that were pretty well known for a long time from a place called Messel in Germany, a little bit younger, about 48 million years old, but still pretty good skeletons. This is in a sort of a lake shale. This is an animal called Palaeontology, and you can see a complete skeleton, a little bit jumbled, but in pretty good shape. Oceanicterus, another bat from this place in Messel. The head has come off of this one, but the rest of the body is here, and the head is drifted off over here, but it's still a pretty complete thing. And then Archaeonicterus, which also is from Messel. So there's at least 3 different families of bats from about 48 million years ago in Germany that are well preserved and well represented. And then finally, the Echolocation, which I'll get back to in a second, that was described here from North America in 2008 by me and some colleagues, and the one that Kevin came and talked to you about. It also is from the Green River Formation. And in fact, the Green River bats really have an advantage over all of these Messel bats in that they're not really very crushed. I mean, there's a little bit flattened, and we'll see in a minute that's true of the skull. But generally speaking, all of these are really pancaked, and it's very hard sometimes to be able to do very much with them, except say, wow, isn't that a very pretty specimen? So, but typically, bats are not beautifully preserved like that. In most deposits that they are preserved, and it's not often that they are, they're much more fragmentary. So there's things like these. This is a jaw of a fossil bat from Africa. These are from Europe. These are from North America. This is from Europe. This is from Africa, and it's a bit of a skeleton, but it's pretty badly broken up. There's a humerus there, and here's an X-ray of it showing the skull here with the ear regions and so forth. But in general, let me just put the other. This is the new family that we're just describing. Also, in general, we're working with a lot less material, and so it becomes sort of problematic in some cases if these are even bats or not. They share with bats a lot of dental features, and we think that they probably are because some of them seem to be represented by modern analogs and look very similar. But someone could make a case, why is that even a bat? I mean, it's a bit argumentative at some level, although I think there's enough shared derived characters to place all of these things within bats, but we don't have skeletons to definitively prove that. So just to summarize a little bit, almost all of the members of early bats, the skeletons I showed you from the Green River and from Messel and so forth, are all archaic forms, and we don't really know how they relate to any of the modern groups. They don't seem to relate to any of the modern groups in any way that we know of. So we have, this is just a distribution of the number of taxa that we know from various time periods, from various parts of the world, and you can see that obviously by the Pleistocene we're starting to get pretty good records of fossil bats in a lot of different places. Miocene records are pretty good, but previous to that, not so much. I mean, the Oligocene is okay, and then as you go to look at the percentage of extant genera amongst all of these fossil forms, you can see that by the Pleistocene things have we're almost up to 100% of modern fossils of modern forms, and so it's a change basically from the Eocene, where you have almost all archaic forms, into the Oligocene, where you start to get some modern things, and by the Miocene and on up, the fauna is pretty modern, even though it may not be well represented in some places. Okay, so let's look at some stories of fossil bats just to kind of get a feel for some of the things we've been able to learn over the years about these creatures. Pardon me for just one moment. So I mentioned CT scanning and showed you some images of the Parapithecus skull spinning in space. We've been able to do some CT scanning of fossil bats as well. This is the Echolocation that Kevin Seymour talked about in the past. This is from 52 million years ago in Wyoming, from the Green River Formation, 51 million, give or take. And unlike modern bats, this animal still has claws on all of its digits. You can see there's the thumb, these are all the fingers. And so that's one thing that makes an Echolocation pretty primitive. if you look at the proportions of the femur and the tibia and radius and humerus and radius, and compare those with modern forms, you can see that Echinonictris sort of has an intermediate relationship between the fore and hind limbs compared to modern bats, where these are all modern forms here. These are all animals that don't fly, and these are mostly animals that have long forelimbs, like gibbons and sloths and things like that. And so Echinonictris kind of fits in between animals that have elongate forelimbs but don't use them for flying, but are instead use them for either brachiation or just slow climbing, and all of these bats. So it really is a transitional form in many ways. And it has some very primitive features about it that make it a very interesting candidate as the earliest, most primitive, well, at least as the most primitive bat we know. Some other things we can do by looking at these animals with X-rays or with CT scans is look at, this is a modern bat, and it's just showing you, I talked about the cochlea before, the ear region of bats, and one of the things that's changes in animals that echolocate is this part of this cochlea on the inner part of it becomes enlarged, basically, as a sort of a larger echo chamber, if you will, or at least a larger processing chamber for signals that come in from echolocation. So you can compare the width of the turn, the first half turn of the cochlea, to the width of the base of the skull, and get a sort of a measurement of animals that echolocate versus those that don't. And so if you look at that, basically here's our basic cranial width on one axis, on the x-axis. That's just basically the width of the skull in its most maximum extent, and then the cochlear width here. All of these forms up here, the little blue diamonds, are all echolocating animals, and the stars are, the triangles down here are modern theropods or non-echolocating forms, basically. And most of the fossil bats that we have, that I showed you the pictures of, kind of fall in here in this cloud of echolocators, but just barely. And then Echinonictris seems to not echolocate, or at least it falls out with those that don't echolocate. So that's something we knew about the animal from before. But something else that we wanted to try and do is to look at the teeth. Now you think about these nice skeletons that are found in lake deposits mostly. The problem with them is that they're all put together. So it's hard to look at the joints. It's hard to look at the teeth because the teeth are in occlusion. So you can't really see the tooth surfaces. And for those of us who do mammal paleontology, teeth are like, the holy grail. They can tell us a lot about the animals. And without being able to see the teeth, it becomes really hard to at least be able to see the tops of the teeth or the occlusal surfaces of the teeth. It becomes hard to say a lot about what the animal might have been eating, maybe even what it might have been related to in terms of other species. And so one way to get at that without actually preparing the fossil, we actually talked about preparing an Echinonictris and taking one of the jaws off at one point. Kevin was willing to do that if we thought it would be a good thing to do. And in the end, we decided we would try to do a slightly different technique first. And so basically, we CT scan this creature, and this is the bottom of the skull, basically, in an X-ray or in a CT image. Here are the two jaws. Here's the edges of the upper teeth sort of sticking out here on the sides, and here's the upper canines and so forth. And the thing we wanted to try and do was digitally remove one of these jaws so we could actually see the teeth, the tops of the teeth. And it turned out to be an enormously tedious undertaking. So here's an upper molar, part of an upper molar, like here, and this is a part of a lower molar in the CT scan. And we scanned this, and there's about 1,800 slices through this animal, and we had to go slice by slice and hand digitize each of the outlines of the lower and upper teeth, so that when we were done, the computer program could take all this information and produce an image with all of those slices stacked up on top of one another and separated from each other. So it was a very long process. There was a woman in Germany who spent months doing this, and without her, we would have never accomplished any of this probably. So anyway, so just to show you, we start out with kind of a rendered image, a mesh multiply a mesh file image of the skull. If we zoom in on it, we can identify the blue as the lower teeth and the sort of white are the upper teeth. And then if we magically remove all the parts that aren't teeth with all of our scanning technology and all the time spent, and we get rid of, say, the lower teeth, and then we have uppers. And we can see, this is what you can basically see from the original view, but we can then turn that around and we can start to see the surfaces of the crowns of the teeth. And so here's this is an outer surface, and it goes in, and you can see one thing we discovered right away was it was a good thing we didn't try to prepare this specimen, because all the inner halves of these teeth are crushed into tiny little pieces. So if we'd taken the jaws off, we wouldn't have gotten any more information than we got here, except that they would have been destroyed completely probably. So that was the good part. The bad part is you still can't see a lot, but we could see more details of the occlusal surfaces, at least about halfway to the inner part of each tooth. And the third molar is pretty complete. We can tell some things about that. Unfortunately, the premolars are pretty crushed, at least P4, which was the one we really, or P5, if you will, the one we really wanted to see. And then these are pretty complete. So at least we could see some more details on these parts of the teeth. And as it turns out, if we did this with the lowers, I could show you the lowers. I don't think I have them here. We were able to identify some features on this set of teeth that go along with the primitive nature of the wings and the skull to suggest that this really is a very primitive animal. And so it was a useful exercise, even though it was a very difficult one to try and do. Okay, so that's one thing we've been able to determine about the fossil record of bats, is that Echonyctris, at least, is very primitive and is getting back to a form that's kind of transitional between bats and whatever the ancestor of bats turns out to be. There's some other things we can learn from the fossil record. We can learn a little bit about bat behavior, and one way to do this is by looking at proxies, at some other kinds of animals that might tell us something about bats. And one of them are these green lacewings. I don't know if Bruce Archibald came here and ever talked about this, but it's a very cool project he's been doing. He's has been looking at these for a long time. Lacewings are common garden insects today, and you see them all over the place. They hunt other insects, so they're kind of handy to have around your garden. And they also are a very favorite prey of bats, who like to eat them. And so it's a fortunate set of circumstances that we actually have a fossil record of lacewings. And why is that interesting? Well, there's a lot of things going on here in this slide, and I'll try to piece them out a little bit so you can see. So basically there's three different families of lacewings, or subfamilies. We're only going to be interested in two. These chrysopines and these nothochrysenes are the two groups that we're most interested in. And nothochrysenes, this is the modern distribution of nothochrysenes today. You can see it's fairly limited, mostly to Europe and some coastal areas. And modern chrysopines are pretty much everywhere around the world today. But in the fossil record, if you go back, these boxes indicate mean annual temperature changes through the sequence, starting about right here at the early Eocene on over to the right, basically. So mean annual temperature is fairly low. It goes up as you get towards them. It goes up to a maximum at about the beginning of the Middle Eocene, tapers off, kind of goes up and down, and the little dots represent the fossil lacewings that we find. And so the red indicates the nothochrysenes, and the blue indicates the chrysopines. And what's interesting about them is this, that the nothochrycene group does not have what's called a chondrotympanic organ up here, chondrotonal organ, but these other guys, these chrysopines, do. And the reason that's interesting is because they use this chondrotonal organ to detect bat frequencies, bat echolocation calls. And if you look at modern chrysopines today and you put them in an experimental format with bats flying around, as soon as they detect a bat echolocation signal, they just stop and drop, basically. And so they practice a sort of avoidance behavior that allows them to avoid predation by bats. And if you experimentally remove this chondrotonal organ, this little bump up here from these guys, the mortality rate goes up to almost 100%. If they have the chondrotonal organ, it drops to about 30%. So it's a pretty significant change in their ability to sort of detect bats and avoid predation. And lacewings aren't the only group that does this. Many others, moths and things, also have sort of radar detection or sonar detection devices, and some of them even send out sonar blocking signals. It's a very interesting arms race that's developed between bats and insects over the course of time. But what's interesting for our purposes is about the same time that bats are starting to diversify in this Middle Eocene time frame, that's exactly the time when chrysopenes show up in the fossil record. And so even very early on, it's become sort of apparent that we know for sure that if these animals are in the fossil record and they actually have these chondrotonal detecting devices, that they must have been having been fed upon or being preyed upon by bats as far back as at least the late Eocene, if not earlier. And so it tells us that the bats were becoming pretty adept at hunting on the wing by that period of time. And so the modern style of hunting that bats practice today was in existence, at least by probably the late Middle Eocene, if not earlier. So by proxy, we can say that that there's evidence that bats were doing some interesting things even back 50 million years, give or take. Okay, so what about some other things that we can tell about bats? One of the things that we talked about early on was that bats are pretty small. And one of the reasons for that, I mentioned the metabolism issue. If you look at modern animals today and you track their metabolic rate versus their body size, elephants, again down here, as you get very large, your metabolic rate slows down, and as you get smaller, your metabolic rate goes way up. So shrews, if you know a shrew, they are just like racing around all the time. Their metabolism is really high, and they have to eat almost constantly to feed that engine. Otherwise, they will run out of energy and basically pass away. And that's why they don't live very long, for the most part. And that's really mostly a property of body mass. If you're a very small animal like a shrew, you have a lot of surface area for a very small amount of body mass, and so you're losing heat through your body all the time. And the only way to maintain body temperature is to really be cranking your metabolism all the time. Whereas if you're an elephant, even though you're very large, your surface area to body mass is not that great, and so you're retaining a lot of heat, and so you don't really need to have a high metabolism to maintain your body core temperatures so much. And so it allows you to slow down and also allows you to live a lot longer. So bats are weird in this way because we talked about before that they live a long time, but they also have a very low metabolism for a very small animal. And this probably has to do mostly with the advent of flight and some of the physiological changes that happen in the ways in which muscles are distributed across the body, and minimizing the loss of core body temperature by simply moving all the muscle masses up to the sort of proximal ends of the bones. And so there's not a lot of heat loss going on out of the legs and so forth because there's no muscle down there really to provide heat loss. There's only just tendon and so forth. And so there's lots of sort of physiological things that are responsible for the fact that bats have a very low metabolism. So what does that mean in terms of their body mass? Well, through a lot of experimentation, you can look at various features of bats. One of the things that are commonly looked at are the frequency of wing beats, just the frequency of a flap, versus the pulse repetition rate, in this case referring to the echolocation pulse that the bat sends out and receives, and then echolocation frequencies, which bats can moderate and change sometimes as well. And as it turns out, all of these features are inversely proportional to body size. So if you are big or bigger, your wing beat frequency goes down, your pulse repetition rate goes down, echolocation frequencies become sort of more confined, which means that you can fly, but you're not really particularly maneuverable. And if you're sending out very few echolocation signals, it makes it very difficult to hunt, especially insects on the wing. So it's turns out that it's much more advantageous to be small and be able to increase the wing beat frequency and pulse repetition rate especially, so that you can not only detect small animals on the wing, small flying insects on the wing, but be able to be very quick and maneuverable to go grab them. And if you see bats flying today, they dart around all over the place, and the reason that they're able to do that is because they're quite small. So, is that part of the initial radiation of bats? Well, Norberto Giannini, a grad student of mine from a while ago, suggested we start looking at the distribution of bats through time, just the size of bats through time, just to see what it tells us. And as it turns out, all of these early forms, Echolocation, even Echolocation, which is fairly small, are still pretty large by comparison with modern bats. So what we have here is a molecular tree of bats with some morphological information impressed upon it. Basically, we used a molecular backbone to root this tree to produce the families that are most well supported by molecules. And then we looked at what happens through each of these lineages in terms of body size. And an up arrow means that they got larger, a down arrow means that they got smaller. And as it turns out, an Echolocation, for example, has a body weight, we estimate, of around 40 grams. And most of these other primitive taxa have also fairly large body weights. And so it looks like the entire bat radiation underwent what we call phyletic nanism. That is, they got smaller at the base of the tree or the clade that represents all the modern taxa. So we know that, for example, that at the base of this tree, the taxa that are most primitive are all small, and they all represent about the mean body size of about 14 grams. And so it seems like there was a decrease in size from the earliest bats to the most archaic ones to the bats in the fossil record that represent modern taxa, at least to begin with. And then things change, obviously, as you go up through the clade. Some get smaller still, some get larger. There's not a clear pattern. As you can see, it's about equivalent in terms of the number of lineages that show some kind of body size increase versus those that show some sort of body size decrease. But what it really tells us is that the ancestor of modern ancestors of bats may not necessarily have been a tiny little creature. It suggests that maybe they were a little bit bigger than we thought. So maybe we need to change our search image a little bit about what what the ancestor of bats was like. And so it was a useful exercise in looking at the distribution of one particular feature over the tree of bats here, the tree of life of bats. So in conclusion, for the life size thing, it was pretty obvious that the earliest forms had relatively large body masses. There was a cross-clade phyletic nanism that occurred, and it just got smaller. And then the body mass established by early chiropterans after the initial nanism was common in the ancestor of things like Palaeochiropteryx, this messel bat. And so we have mostly all of the early bats that are above the very base all started out at the same place at about 14 kilograms, as far as we can tell. Okay, so I put this up here. Keep this date in mind because we're about to get back to sort of a final sort of summary of what we know about the modern history of bats and the fossil history. So we're looking at something around 50 million years for this change in body size distribution, and also the changes that we talked about before about the lace wings and various other things. They all seem to be coalescing at around this 50 to 52 million year old date. So, all right, so what about, after all of this, what about the origin of bats? You may have seen this in Nature last year. This is an animal called Echi, as I understand it's pronounced correctly. And I thought this would be appropriate for Drumheller because it clearly is not a bat, but it is a animal that was described. And the interesting thing about it is, we know that the birds and some dinosaurs are related in some way or another. But this is an animal that apparently had a patagium, just like a bat. Apparently had long fingers, just like a bat. as you can see here. So it was flying in a completely different way than sort of birds. And so all of a sudden we've now added another sort of vector within reptilia or within aves, whatever these creatures actually, I think it's an aves of some sort, for yet another way in which they were taking advantage of the air. And obviously I'm not suggesting that Chi, or whatever it is, was an ancestor to bats, but it does show that this same kind of morphology and this same kind of adaptive pattern happened at least one time more than just in bats. And so it's an interesting sort of example of convergence between animals that are clearly not particularly related otherwise. So, okay, so that doesn't really help us with bats, obviously, but what about the bats? So this is the molecular tree we looked at before. Actually, it's a slightly modified version thereof with divergence times located along this Cenozoic time axis from 65 million KT boundary up to modern times. And this is the radiation of bats. And as I mentioned before, the suggested divergence time is about 64 or so years, give or take. And here's the Paleocene-Eocene boundary at about 55 million years. And that's interesting because lots of modern groups of mammals show up about this time. Primates, paracerdactyls, artiodactyls, all the modern orders show up at about 55 million years ago. And here's our range of about 52 to 48 million years ago, where we start to see modern bats finally showing up. So there's a bit of a gap here obviously between 65 million and even between the Paleocene-Eocene boundary, where many of the modern orders of mammals show up, and then bats showing up, at least bats that we are sure are bats a few years later, or a few million years later. So what does that mean? Well, here's a different look at that same time slice. And it's here again starting at 65 million. This is the Paleocene here up to about 55. This is when 55 million is when sort of many of the modern groups started to show up. And here's where we have Echinonictris slots in at around 51 or 52 million years. And that's the one we know is a bat. We've got the skeleton of it and so forth. And, there are other potential bats down here from places in India and Europe that are older, at 54, 50, but nothing quite as old as 55 million. So there's a big, what I call bat gap here, of supposed time when bats first arose, if molecular data is correct, and the time where we actually start finding obvious bats in the fossil record. And that's in this time frame here. Obviously, one of the problems is that without complete skeletons, it's very difficult to know what's a bat and what's not, and we don't even know for sure what might have constituted a bat, an intermediate bat. We have some hints with the Echinonictris, but we don't know what came before that exactly. And these animals are all potential bats, but they're known only from teeth for the most part, and so a little hard to know for sure. And interestingly, right at the Paleocene-Eocene boundary, at 55 million years ago, there's a locality in Europe called Durham that has obvious primates in it, has obvious artiodactyls, has obvious paracerdactyls, and it has literally hundreds of thousands of specimens of teeth, tiny little teeth of insectivores and things, not one single one that looks like a bat. So that seems a little bit odd to me. It almost suggests that bats simply weren't living, at least in Europe, 55 million years ago. So where were they and where did they come from? So one of the things that happened, here's our little time window again, is that if you look at the mean annual temperature record, basically for this time frame from about 52 up to 48, you can see there's here's the sort of blip of increased temperature at the Paleocene-Eocene boundary I talked about at 55 million, and then there's a gradual, it sort of tapers back, and then it goes back up again to an increase into what's called the early Eocene climatic optimum at about the beginning of this time period that we're looking at. So it seems like there's if bats existed in this time frame, they probably weren't really exploiting the kinds of niches, the kinds of doing the kinds of activities that we've come to recognize bats doing today, because there doesn't seem to be much evidence of that yet, until we get to about 52 or 51 million years, when all of a sudden we've got green lacewings that are avoiding bats by detecting their echolocation signals. We've got decreases in body size showing up here, and we've got the sort of modern bat family starting to show up at that same time period. So it seems like if bats were around earlier than this, we might simply never be able to find them, because we might not be able to recognize them as such. And it's only after they start becoming or doing the things that make them bats that we would recognize them in the fossil record. What does that mean in terms of what we may expect to find? Well, this is kind of a way in which it was visualized by one person, this guy Smith, in 1977, of the changes that might occur in bats. And there's an animal that has, a patagium with a few little webbed fingers and so forth here, and then as you progress through the evolutionary sequence, a little bit more elongate, finally something like this, and then ultimately a bat with a hand wing, sort of like modern bats. And I would say that if you were to put an Echonycteris into this series, it fits pretty much right here. We have an animal that still has claws on all of its digits, and this was visualized, 30 years before an Echonycteris was discovered. And an Echonycteris really falls into this pattern right here very nicely. Had sort of shortish forearms and so forth, but we really lack all of these. And the question is, will we ever find them? I don't know. I have a funny feeling that going from something like this to something like this probably happened fairly rapidly, and it may be beyond the resolution of the fossil record to actually do that. But what we really need are some more localities in the Paleocene or in the earliest Eocene that preserve lake deposits, because it seems like bats hang around lakes a lot because there's a lot of insects. And the best way to get good bat skeletons is if they crash and fall into these lakes and get preserved.
Nocturnal mammals
what happens in bats?
That over time adapted. What were once just limbs eventually became wings. Now they could hunt throughout the forest, but
No, that's a fanciful, imaginative way of how it might have happened. But the truth is we still don't know, and we're still looking, and I think I'm going to stop there and take some questions. So thank you very much.